Most of us grew up with a fairly simple picture of the solar system, 8 planets neatly spaced, tracing quiet circles around a stable sun. Perhaps you remember the diagrams in textbooks or the little models hanging from classroom ceilings, clean, orderly, almost elegant. But prepare to have your perception of our cosmic neighborhood shattered, as we uncover the astonishing truth about how our solar system truly moves through the universe. Because the solar system is not sitting still, it's not even close. And understanding its actual motion, and how we manage to figure it out, is one of the most remarkable journeys in the history of science. To begin, let's consider what is actually happening at any given moment. While the planets orbit the sun itself isn't fixed in space. It's constantly being tugged by the gravitational influence of its massive neighbors, particularly Jupiter and Saturn, causing it to wobble around a shifting center of mass within our solar system. Simultaneously, the entire solar system is hurtling through the Milky Way at approximately 230 kilometers per second, completing one full orbit around the galactic center roughly every 225 million years. And as it travels, it doesn't glide along a flat, stable path. Instead, it gently bobs up and down through the galactic plane, much like a horse on a carousel, oscillating above and below the central disk of the galaxy on a rhythm of roughly 60 to 70 million years. Layer on top of that the fact that the Milky Way itself is moving through space, drawn towards colossal structures like the Virgo cluster and the Great Attractor, and the picture becomes almost incomprehensibly dynamic. But this is where things get philosophically interesting. Is this motion real in any absolute sense? Imagine you're sitting on a boat crossing a wide river. From your own perspective, you might feel perfectly still, with only the water slipping past the hull to give any sense of movement. A person watching from the shore, however, would observe you moving both across the current and downstream, tracing a diagonal line through the water. And someone watching from a satellite far above would see the entire river itself winding through a rotating Earth. None of these perspectives is wrong, they are simply different frames of reference, each one accurate and valid within its own context. This fundamental principle in physics, formalized by Galileo, applies just as powerfully to the motion of our solar system. Depending on where you position your imaginary observer, the solar system appears to be doing completely different things. There is no single absolute answer to the question of how the solar system moves, only a set of answers that depend on the vantage point from which you are asking. This then raises an even more fascinating question: given that we are trapped inside this system, looking outward, how did we ever manage to figure any of this out? The story begins, as so many stories in astronomy do, with the basic question of what orbits what. For most of human history, Earth was assumed to be the center of everything. The sky rotated above us, the sun rose and set, and the planets drifted across the heavens in patterns that were observed and recorded for thousands of years, but never fully explained. It was Nicholas Copernicus who, in the 16th century, proposed the radical idea that the sun, not Earth, sat at the center of the planetary system. This was not merely a correction of detail, it was a fundamental shift in how human beings understood their place in the cosmos. Earth became a planet among planets, orbiting a common center just like everything else. That framework was then sharpened dramatically by Johannes Kepler in the early 17th century. Kepler had access to extraordinarily precise observational data collected by the Danish astronomer Tycho Brahe, and he used it to demonstrate that planetary orbits are not perfect circles, but ellipses, with the sun located at one of the 2 focal points of each ellipse. He went further, showing that a planet's speed is not constant, it accelerates as it swings closer to the sun and slows as it pulls away, always sweeping out equal areas of its orbital path in equal spans of time. And he identified a precise relationship between a planet's distance from the sun and the time it takes to complete one orbit, a relationship that holds true across every planet in the solar system. These 3 laws were not just descriptions of planetary motion, they were the first real hint that the solar system operates according to deep mathematical rules. Isaac Newton then took those rules and asked why they existed. His answer was universal gravitation, the idea that every object in the universe attracts every other object with a force that depends on their masses and the square of the distance between them. This single principle, captured in the formula F equals g times, explained Kepler's ellipses, accounted for the varying speeds of the planets, and predicted the minimum velocity a body needs to maintain a stable orbit rather than spiraling inward or escaping outward. For Earth, that velocity is roughly 30 kilometers per second. Newton's work also revealed something crucial about the solar system's internal structure: the Sun does not sit perfectly at the center of the system. Rather, the Sun and its planets orbit a shared center of mass, a point called the barycenter, which shifts constantly depending on the positions and masses of the planets. When Jupiter and Saturn align on the same side of the solar system, their combined gravitational influence can push the barycenter entirely outside the visible surface of the Sun. The solar system, in other words, does not orbit a stationary star, it orbits a moving point in space, and the star moves around that point too. With that foundation in place, astronomers began to reach outward towards the broader galaxy. In 1838, Friedrich Bessel accomplished something that had eluded scientists for centuries: he measured the distance to a star. His technique, called stellar parallax, relied on a surprisingly simple geometric principle. As Earth travels along its orbit, nearby stars appear to shift slightly in position against the background of more distant ones. By carefully measuring that apparent shift from opposite ends of Earth's orbit, Bessel could calculate the actual distance to the star in question. This was the first reliable method for determining how far away individual stars truly are, and it gave astronomers the tools they needed to start mapping the structure of our galaxy and understanding where our solar system sits within it. 4 years later, Christian Doppler described a phenomenon that would become one of the most powerful instruments in all of astrophysics. When a source of light moves toward an observer, its waves are compressed, shifting toward the blue end of the spectrum. When the source moves away, the waves are stretched, shifting toward the red. By analyzing the spectrum of light coming from distant stars and galaxies, astronomers could determine whether those objects were approaching or receding, and at what speed. This Doppler technique allowed scientists to measure the velocities of stars relative to our solar system, giving them the ability to trace out the orbital motion of the solar system around the galactic center and to map the overall dynamics of the Milky Way in 3 dimensions. Over the following decades, 2 more developments transformed the picture further. Edwin Hubble's observations with the Hooker telescope at Mount Wilson revealed that the faint smudges visible at the edges of the sky were not clouds of gas within the Milky Way, but entire galaxies in their own right, all of them moving away from one another in an expanding universe. Around the same time, Carl Jansky discovered that the Milky Way emits radio waves, allowing astronomers to probe the structure of our galaxy through regions too dense with dust for visible light to penetrate. These radio observations helped locate the concentrations of mass within the Milky Way that drive the solar system's vertical oscillation as it orbits the galactic center. Then, in the 1970s, astronomer Vera Rubin uncovered something that no one had predicted. She was studying the rotational speeds of stars within galaxies, expecting to find the same pattern seen in our solar system: stars close to the center moving fast, stars far from the center moving slow, their velocities falling off smoothly with distance. Instead, the outer stars were rotating just as quickly as the inner ones, creating flat, consistent curves that made no sense given the amount of visible matter present. Something else had to be providing extra gravitational pull. That something was eventually named dark matter, a form of matter that neither emits nor reflects light, detectable only through its gravitational effects on the things we can see. Current estimates suggest that dark matter makes up the majority of the total mass in the universe, forming vast invisible halos around galaxies, including our own. As the solar system orbits the Milky Way, it is almost certainly moving through one of these halos, its trajectory subtly shaped by matter we cannot directly observe. And that is where some of the most difficult questions begin. We do not yet know what dark matter actually is. We do not know precisely how it interacts with ordinary matter beyond the pull of gravity. We have theories, several competing ones, but no direct detection. Similarly, while Einstein's general theory of relativity describes gravity with extraordinary precision across cosmic scales, it breaks down at the extremes, inside black holes, at the very earliest moments after the Big Bang, in conditions where quantum mechanics and gravity collide in ways we do not know how to reconcile. The motion of our solar system through space is, in a sense, a physical record of all these forces acting simultaneously across billions of years. Reading that record has taken centuries of observation, mathematics, and imagination, and the record is still not fully understood. The solar system is not simply drifting through an empty void. It is threading through a living, gravitationally complex structure, tugged by invisible mass, oscillating through a spinning disk, caught inside a galaxy that is itself accelerating towards something larger. Every answer astronomers have found has come wrapped in a new question, and that pattern shows no sign of stopping.